Over the next few videos we will cover the unit cell and its use in X-ray crystallography. First, a quick introduction. X-ray crystallography is a very powerful method of determining the 3D arrangement of molecules in a crystalline material. The structure is determined by use of X-rays which are diffracted through a single crystal of the molecule. The way in which the X-rays are diffracted indicates the positions of the atoms in the molecule. However, the entire picture is needed to place each atom in the structure, as each part of the pattern is intrinsically linked to every atom. In order to make these calculations, we first need to work out the unit cell. The unit cell is defined as the smallest repeating unit of the cell required to build up the crystal structure, which simply means that it's the smallest template that still represents a whole crystal. The unit cell can include very many or very few molecules, and is the first thing that we need to work out to determine the structure. This is done with a quick exposure to X-rays. However, this is when we start to encounter some more complex calculations, so I will try to keep it simple. Using the cell parameters, sizes, worked out from the diffraction pattern, we first work out how many molecules are present in the unit cell. As, in some cases, a crystal will form with the solvent the molecules originally dissolved in. From the unit cell we can also derive the asymmetric unit. This is the smallest repeating unit, regardless of crystal structure. The asymmetric unit will usually be a fraction of the unit cell. Once the unit cell is derived, the crystal is exposed to thousands of separate X-ray beams. During this time, the crystal is rotated up to 5 degrees side to side. This ensures that all lattice planes have been fully diffracted and each spot is recorded. We are now in the process of working out the crystal structure. Now we must work out the absolute positions of the atoms and the bond lengths to gain full detail of the molecular structure. When the diffraction pattern has been recorded, we must now overcome the biggest problem with X-ray crystallography, the phase problem. This is a problem that when waves are scattered, it is only possible to detect their intensities on the detector. The relative phase cannot be worked out, and so the wave cannot be traced back to its original point of scattering. Firstly, we need to complete a Fourier transformation. Fourier was a very important mathematician around the end of the 19th century. He worked out that waves could be deciphered by turning them into complex numbers. He used sine and cosine to create a single notation for the wave's amplitude and phase, while still making it accessible information, essentially simplifying the maths without affecting calculations. This gives a very clear diffraction pattern, which is useful for defining the symmetry groups in the crystal. It is a symmetrical distribution of the diffracted waves. By creating this Fourier transformation, every reflection is now important to the structure, as every reading is equated to the entire molecule. Single atom positions cannot be decoded, only the entire unit cell. It is, however, now that we encounter the phase problem when we go to decode the transformation. As we try to reverse the Fourier form, we once again come to see that the phases are unknown. This problem has taken 2 Nobel Prizes to solve. The first scientist to come up with a solution was Dr. Patterson, an American physicist, and his solution is known as the Patterson synthesis. It works very well for molecules with one or few very electron-rich atoms, such as heavy transition metals. The Fourier transformation is once again used. However, because the phases are unknown, they are set to 0, essentially cutting them out of the equation. Although this seems like a very clunky shortcut to the equation, it is actually very clever, because now what we see is a deviation from the average electron density. This is why it works so well for electron-rich nuclei, as they have a very large difference. The resulting electron density differences are displayed in 2D form, with contour rings, just like a geographical map. From this map, it is easy to see areas of high density. However, these maps show how atoms are arranged relative to each other, not their position in the molecule. Once the regions have been defined, we can run the Patterson map again, without the signals from them. Now we see electron density difference from the other molecules. If there are halogens or heteroatoms, we will see these now. If not, we will just see the electron density peaks for any carbons, as these are much more electron-rich than hydrogen. Once this has been done, we have a rounded picture of the molecule in the unit cell and have to place the hydrogen atoms in ourselves. As I said earlier, it's a very useful method for any molecules with electron-rich centres, and is still used for these scenarios as it's much faster. The 2 major problems with the Patterson synthesis are when there aren't electron-rich centres, there are hardly any difference in the electron density. And the second problem is that peaks can be overlapped if not well resolved, i.e. if they are both too close together, or both too close to the average electron density, or that large regions of the map can be left without any defining features due to similar electron densities across the unit cell. However, due to these problems, there is now a new direct method approach. This is a method that took 2 Nobel Prizes to get right. For this method, we must restrict the parameters to our advantage. We know that the electron density must be either 0 or positive in the unit cell. We also know that the electron density has to be localized around atoms. These parameters we use to work out the structure. The thought process runs like this. All the waves have both positive and negative sections, and we must add up these waves so that the positives superimpose and the negatives are left blank, as we know that the electron density cannot be negative. We now follow a very methodical procedure. Firstly, the most intense reflections are picked, and a probable relationship between their phases is decided upon. It's a guided form of trial and error. However, with practice it comes together. Once the estimated phases are ready, they are combined with the amplitudes, which can be measured, to create an electron density map. From this map there should be key features that reveal the atoms. If there aren't any, then another set of phases are tried. From these key features we can pick out atoms that build up the basic structure. From here we can now refine the structure. We can only compare the amplitudes. We do this with the method called least squares analysis, which means that the difference between the squares of the amplitude values can be compared and used to be minimized. Like a 3D line of best fit through all the Fourier parameters. These parameters are the coordinates of the atoms and a displacement parameter. In other words, the asymmetric nature of the electron distribution over the atom. For hydrogen atoms, we can assume that they are fully isotropic, spherically distributed, as they only have one spherical s orbital occupied. However, for other larger atoms with pi and d orbitals, which are not symmetrically distributed, and this must be accounted for during the refinement. Overall, there are 9 parameters that can be refined, and the structure is finally complete.